In the past few years, artificial intelligence has made leaps so rapid they've begun to reshape how we think about intelligence itself. At the heart of this transformation lies a quiet revolution in how models understand and generate language, not through rigid rules, but through patterns learned from vast amounts of data. This isn't just about better chatbots or smarter assistants. It's about a fundamental shift in how machines interpret meaning, context, and even intention. To understand where we are today, we need to go back to the beginning. Early language models were built on statistical approaches, counting word frequencies, analyzing grammar, and relying on handcrafted rules. These systems could parse sentences, but they lacked depth. They didn't truly understand language. They were like translators who memorized phrases, but couldn't grasp nuance, sarcasm, or cultural context. Then came the breakthrough: deep learning, and specifically neural networks trained on massive text corpora. The real turning point arrived with the introduction of the transformer architecture in 2017. Unlike previous models that process text sequentially, like reading a book from front to back, the transformer used self-attention mechanisms to weigh the importance of every word in a sentence relative to every other word, all at once. This was revolutionary. It allowed models to capture long-range dependencies, like understanding that a pronoun in the middle of a paragraph refers to a character introduced 10 sentences earlier, without losing track. It also made training far more efficient. Instead of struggling with sequential processing, the transformer could parallelize computation across entire sentences, drastically reducing training time. But here's where things get even more fascinating. The real power of transformers didn't come from the architecture alone, it came from scale. When researchers began training these models on hundreds of billions, even trillions of tokens, words and punctuation marks extracted from books, websites, scientific papers, and more, the models began to exhibit behaviors that were not explicitly programmed. They started to generalize. They learned to write poetry, debug code, solve math problems, and even reason through multi-step logic puzzles. This phenomenon is known as emergent ability. It's not that the model was told to write a sonnet. It learned the structure, rhythm, and emotional tone by observing countless examples. It wasn't explicitly taught how to debug code, but by seeing thousands of code snippets and their corrections, it developed an internal representation of what correct code looks like. And now we're seeing the next evolution: instruction tuning. Models like GPT, PaLM, and Llama weren't just trained on raw text. They were fine-tuned on datasets where prompts were paired with desired responses. This process taught them to interpret human intent. Explain quantum mechanics like I'm 5 isn't just a query, it's a directive. The model learns to adapt its tone, depth, and structure based on the instruction. But the most profound shift isn't just in performance, it's in the nature of the model's knowledge. Unlike traditional software, which is explicitly coded, these models store knowledge in the weights of their neural networks. The information isn't stored as discrete facts. It's embedded in complex, distributed patterns across millions of parameters. This means the model does look up facts. It generates them based on statistical likelihoods derived from its training data. This raises a critical question: how do we know what a model actually knows? When a model says, the capital of France is Paris, it's not retrieving a memory. It's predicting the most probable next word given the context. And if the training data contains errors, or if the model is exposed to misleading information, it can generate plausible-sounding falsehoods, hallucinations. So how do we fix this? One approach is retrieval-augmented generation. Instead of relying solely on internal knowledge, the model can query external databases or knowledge graphs in real time. It checks facts before generating a response. Another strategy is to use smaller, specialized models, expert models, that focus on specific domains like medicine or law, reducing the risk of overgeneralization. But the future isn't just about fixing flaws, it's about expanding capabilities. We're now seeing multimodal models that process not just text, but images, audio, and video. A single model can describe a photo, transcribe speech, and generate a summary all in one pipeline. And with the rise of autonomous agents, models aren't just answering questions, they're planning, acting, and learning from their environment. This is where AI begins to resemble cognition, not because it thinks like a human, but because it can simulate complex behavior. It can set goals, break them down into steps, use tools, and adapt based on feedback. These agents aren't just passive responders, they're proactive problem solvers. Yet as capabilities grow, so do the challenges. The energy required to train large models is staggering. Some models consume as much electricity as a small town over the course of training. There's also the issue of bias. If a model learns from the internet, it learns the biases embedded in human language, gender stereotypes, racial prejudices, cultural assumptions. Mitigating this requires careful curation of training data, algorithmic fairness techniques, and ongoing human oversight. Still, the progress is undeniable. From simple pattern matching to systems capable of creativity, reasoning, and adaptation, we've moved from rule-based systems to models that learn from experience. And the most exciting part: we're just beginning. The next frontier lies in efficiency, making models smaller, faster, and more energy-conscious. Inference optimization, quantization, pruning, and distillation are techniques that allow us to compress massive models into lightweight versions that run on mobile devices or edge hardware. We're also exploring hybrid architectures, combining symbolic reasoning with neural networks to create systems that can both learn from data and reason logically. Ultimately, the goal isn't to replicate human intelligence, but to build systems that can augment it. To help us solve problems we couldn't solve alone. To explore scientific frontiers, accelerate innovation, and deepen our understanding of the world. So as we stand on the edge of this new era, one thing is clear. The way we interact with information, with tools, with each other, is being rewritten, not by humans alone, but by machines that learn, adapt, and in their own way think.